Okay, so what we're going to do here is we'll finish up the friction that we started on Wednesday, excuse me, and we'll move on to centripetal motion and centripetal forces. So, as we mentioned on Wednesday, whenever one object attempts to slide over across the surface of a second object, it encounters a certain amount of resistance in the form of frictional force. The frictional force always points in the direction that is opposite the motion or the attempted motion. In the case of a small force, if the small force is less than the maximum amount of friction that can exist between the object and the surface, then it won't actually move, but the force of friction will still point in the direction opposite of the direction of the push. So when you push an object at rest on any non-frictionless surface, it will encounter a resistive force called static friction. That static friction is another example of a just enough force, what I call a just enough force, in that the surface applies just enough static friction to cancel out your push and keep the object at rest. So if you push just a little bit on it, it will resist by applying the surface will resist by applying a force of static friction equal and opposite to the magnitude of the push. If you push harder, it pushes back harder and keeps the object still regardless of the force that you apply. All right, so that is until you push hard enough. And if you push hard enough, you'll eventually overcome the maximum amount of static friction that that particular surface can provide. When your applied force exceeds the maximum static friction, then the object you're pushing on will experience an unbalanced force because you're now pushing harder than that surface can supply friction for, and the object will begin to move. The maximum static friction of an object on a surface is given by this relationship here. The force of static friction, the S stands for static friction, the maximum amount is given by mu naught, which is the coefficient of static friction, times Fn, or sometimes in the textbook it is written as just little n. That's the normal force. That's the force pressing the two objects together. In this case, it would be the force of gravity pushing down on the mass of the block. All right, so this is the maximum that static friction normally holds. You'll sometimes see static friction Fs is less than equal to mu s times the normal force, because when you only push a little bit, it doesn't obviously push back with the maximum amount all the time, because in that case, when the baby pushes on the block would just run over the baby, and that doesn't happen, right? It always provides it's a just enough force, as we said, and so it provides. If you only push a little bit, it won't provide this full static force. It'll just apply just enough, a lesser amount, just enough to push back on the force and balance it until you hit the maximum available force of static friction. If a particular surface is only capable of supplying some maximum amount of static friction, after which that force of static friction is overcome by the other forces, whatever it is, the push or the pull, and at that point the object will start moving. But and we demonstrated this at the very end of Wednesday with the credit card sliding down the ramp. That once the object is in motion, it generally only has to overcome a slightly lesser force of kinetic friction as opposed to static friction. Let me start that over again. Once it's in motion, the object generally must overcome a slightly lesser force of kinetic friction to further its motion in that direction. So in the case of the credit card, although static friction for that particular incline was enough to keep that card stationary, once I started moving it, it didn't just come back to a stop. It continued to slide all the way down because the force of gravity times the sine of the angle, right? Because on an incline, it's g sine theta, wasn't enough to overcome static friction. But once it was moving, that same g sine theta was enough to overcome the lesser force of kinetic friction. And the kinetic friction, force kinetic friction is just given by the coefficient of kinetic friction, mu k, times the normal force. Just like the static friction, the maximum static friction is equal to mu s times the normal force. Okay. Now we're going to move on to circular motion. So this is a return to the end of chapter 3 that we had skipped earlier. So earlier, previously, we had seen that if the motion that we're dealing with is always parallel to the acceleration, as is in the case when we're just moving in a straight line, right? A car is moving, say, to the west, and it is speeding up such that the velocity is to the west, and so is the acceleration. When the motion is parallel to the acceleration, then the result is just a change in the magnitude of the velocity, but there's no change in the direction, right? If the car has an acceleration to the west and it is moving to the west, then the only thing you can do is speed up or slow down, but not change its direction. I guess with the exception that it could pull a 180 and end up going in the completely opposite direction. But if it's going in east-west, it can not suddenly start going north-south or northeast-northwest. Okay. Later, we saw that if the initial motion is at some angle to the acceleration, then the motion that follows is a curved parabolic path, right? So this is where we were looking at projectile motion, where the acceleration was straight down, because the only acceleration was due to gravity, and that points straight down. But if the motion had been straight up or straight down, then it would just follow a straight line, and it would not change from that straight up, straight down line of motion. But as soon as we angle it a little bit, whether it's just 10 degrees or all the way out to 90 degrees, as soon as we have some angle between the direction of acceleration, downward in this case, and the direction of its initial velocity, we see that it no longer follows a straight line path. It follows a curved path in which its direction and its velocity are changing continuously. Okay, so let's now consider what happens if the motion is always perpendicular to the acceleration. So we're going to start with the simple case of, instead of it being always parallel, we're going to take the opposite tack and look at what happens if it's exactly perpendicular at all times. Okay. So the way to look at this is to consider an object that's traveling in a perfect circle. For now, we'll imagine this to be a horizontal circle, and we're looking at it from above. So this is like something traveling in a perfect circle on a table, and we're looking at it from above the table. So by definition of what the average acceleration is, remember that acceleration is velocity over time. Average acceleration is the change in velocity from beginning to end over the duration from beginning to end, the change in time from beginning, starting point to end point. So delta V is, like we said, V2 minus V1, which we can write is V2 plus minus V. Oh, this should be V1, sorry. Okay, I'm going to correct that. Hold on. All right, so I fixed it now so that it reads properly. V2 minus V1 is delta V. Now V2 plus minus V1 is delta V. So we can do this graphically and see what we get. We have V2, so we look at 2 points in time. Right, at one point the object is moving in a perfect circle. It's at this position, and then its velocity is tangent to that. In other words, it is moving at this moment. If you look at its velocity, it's kind of moving this direction, and if there were nothing holding it into this circular track, there was no string or kind of railing or anything like that, then by Newton's first law, this thing would just continue its constant state of straight line motion and just fly away. But if there is something that is holding it into this circular track, into this circular path, then at some time later, at t2, it will be over here, and its instantaneous velocity will be this kind of lighter green arrow. Again, tangent to the circle right at the point where it's at. And its position on that circle would then be R2 here. Okay, so if we wanted to know, we would say we're interested in calculating what the acceleration is between here and here, between these two different velocities which are pointing in very different directions. Then we would take the definition of average velocity, V2 delta V over delta T, write out V2 minus V1, and let's do this graphically. So we would take V2, but we're going to do vector addition with not V1 but minus V1, which, as we know from chapter 1, is the 180 degree flip of V1, which I've drawn here in yellow or orange. So we can do it this way. We say delta V is V2 plus, and so we go head to tail, we add on not V1 but negative V1, and then delta V is the resultant of that addition, right? The delta V is just V2 plus minus V1. And the resultant always points from the starting point of that entire journey to the end point of that journey if you follow the head to tail path. And so delta V points straight down. Sometimes this is drawn this way with V1 pointing up, V2 pointing down, and delta V pointing from here to here. The way you can interpret this is if you go back to our original equation here, we wrote delta V is equal to V2 minus V1, and then we rearranged that to be V2 plus minus V1, which is what we drew here. But you could easily have rearranged this to say, let's bring this minus V1 to the other side, right? So then it becomes delta V plus V1 is equal to V2. In other words, V1 plus delta V is equal to V2. So then you do head to tail here. V1 plus delta V head to tail. And the resultant of that addition, that vector addition, is from beginning to end, V1 plus delta V. And V1 plus delta V, if you just kind of rearrange this equation, is V2, right? So either way, we see that delta V for this particular configuration of evaluating from here to here on the circle is results in V2 being pointing straight down. And since average velocity is just delta V vector divided by the time it takes for it to get from here to here, then the average acceleration also points straight down for this configuration. On the other hand, if we look at the average velocity, defined as 1/2 of the initial plus the final velocity. Right? If we go back to when we derive some of the kinematic equations, we'll see that this was a valid definition of the average velocity. Right? If you start at, say, 40 miles per hour and you end up at 60 miles per hour, then we all know intuitively that it's your average speed, if you were kind of accelerating uniformly, would be 50, which is, of course, 40 plus 60 divided by 2. Right? All right, so the average velocity is 1/2 of v1 plus v2. Well, v1 points this way. You do head to tail addition, v2 points down this way. The resultant is from here to here. You see that v1 plus v2 points straight to the right. And obviously 1/2 of that would be still pointing straight to the right, but only coming out to here. So the average acceleration points straight downward, but the average velocity points to the right. Okay, we could reevaluate this with a smaller angle, right? So a smaller difference. Everything's here the same. It's just that we've now only let it travel from here to here, and I've chosen them again symmetric around the vertical position just for convenience. If we had chosen something else, then we just rotate our heads. But again, by either way of doing the vector addition, you see that delta v again points straight down. It is, of course, a slightly smaller vector than before, but of course it takes less time to go from here to here than it did to go from here to here, so that the average acceleration again is straight down and has the same magnitude because this is now divided by a smaller time. Let's say this is half the size of the other one, then it took half as long to get there. All right, and if we continue this process, taking the angle between them to be smaller and smaller, right, taking the time that we actually let it travel to be smaller and smaller, then velocity continues to point down, continues to be smaller for smaller durations. And of course, if we take this delta t or this delta theta in the limit that goes to 0, then we've basically achieved finding the instantaneous acceleration instead of the average acceleration. And you see that in that limit, the instantaneous acceleration still points straight down because delta v always points straight down in this case. Okay. The sum of the two, which we use to define the average instantaneous velocity, continues to point to the right. So in the limit of delta t going to 0, the instantaneous acceleration is exactly perpendicular to the instantaneous velocity, with a pointing down and b pointing to the right. And we've now closed up the angle so much that basically it all refers to this one spot right here at the top of the circle. So at this moment, when we are exactly at the top of the circle, the velocity is purely in the x direction, and the acceleration is purely in the y direction. And so it makes sense to just use our typical x, y coordinate system because things break down very nicely in that coordinate system. But what if we evaluate this a moment later? A moment later, if this thing's moving in a perfect circle, it's going to move along the circle over here. Why does it move along the circle? Well, you can see that the velocity wants to carry it off along here, but it's being it's undergoing an acceleration in this direction towards the center, which pulls this thing back from this straight line motion back onto this curved path. So if a moment later it's moved along this circle to this point on the circle, to this point here on the circle, then all three of these vectors, the position vector to this new point, the acceleration vector pointing back towards the center, and the velocity vector pointing tangent to its motion, kind of to the line that is just skimming that point on the circle. None of those are completely along x or y. In other words, all three of these vectors have both an x component and a y component for r. Right? A has an x component this way and a y component that goes from here to here. Same thing for v, x component and a y component. So in this case, maybe the best choice is not these fixed traditional xy coordinate systems. At least is maybe not the only choice. Instead, let's consider using a moving reference frame, one that instead of the reference frame or our axes stay pointing always in the same direction, we let our axes move along with us. So as we move along with the object, we'll call the direction that's parallel to the velocity the tangential direction. Okay, that was what was previously the x direction. But now we're going to let that xy axis rotate along with us. And so as to avoid confusion between the traditional x and y and this new rotated one, we'll call this direction the tangential direction. It's tangent to the curve. And the direction that's perpendicular to that is along the radius, right? So it's in the radial direction. So we'll call that the radial direction. It's in the direction of increasing and decreasing radii of circles. Right? So an object moving in this way, that is moving in a circle without either speeding up or slowing down, is said to be in uniform circular motion. For uniform circular motion, the acceleration is always directed inward in the radial direction. And that acceleration is called centripetal acceleration, which just means center seeking. Also for uniform circular motion, the acceleration has no component along the tangential direction. Right? So the velocity is along the tangential direction, but the acceleration is purely in the radial with no tangential component at all. Now, what would happen if we were to add a component of acceleration along the tangential direction? Well, it wouldn't be uniform circular motion anymore, because by definition, uniform circular motion, all the acceleration is in the radial direction. But what if we take something that's currently moving with uniform circular motion and we added a small acceleration in the same direction as the instantaneous velocity, in that tangential direction? Well, tangential direction acceleration changes the magnitude of the velocity vector. We knew that already from our earlier 1D studies, where whenever we had an acceleration that pointed in the same direction as the velocity, that just changed its speed, right? It sped up the object, changed the magnitude of the velocity, but not its direction. So the tangential component of the acceleration changes the speed, while the centripetal component of the acceleration changes the direction of travel. So in most textbooks, you're just given that acceleration, the centripetal acceleration is v squared over r without any further explanation. But as you know, I like to let you guys see where things come from. Of course, this derivation, you won't be tested on this. You won't ever have to derive this on an exam. But an optional derivation of the centripetal acceleration formula. Okay. So let's consider a situation here where v1 is perpendicular to r1 and v2 is perpendicular to r2, just like we had drawn it before, right? The velocity is tangential to its position on that unit, that circle, that circular track. So v1 and v2 must be the same. The angle between v1 and v2 then must be the same as the angle between r1 and r2. Okay. If these are perpendicular and these are perpendicular, then the change in angle from here to here has to be the change in angle from there to there, right? Because we've basically just taken this whole L-shaped thing and rotated it by theta. Okay, so if the angle between these two is the same as the angle between these two, then these two triangles are similar triangles, if you remember from your geometry. And so with similar triangles, we can go ahead and write that the delta V over V, which would be either one of these or the average of the two when as you shrink delta V to 0, has to be the same as delta R over R. Or if we manipulate this slightly, then delta V is equal to V times delta R, right, bringing this guy up here, over R. Okay, so our definition of average velocity, or I'm sorry, average acceleration is just delta V over delta T, right? The magnitude of delta V over delta T gives us the magnitude of the average acceleration. We already figured out what delta V is over here, so we just take that whole thing and divide it by delta T, V times the magnitude of delta R over R delta T. And if we take this in the limit that delta T goes to 0, this just is just instantaneous velocity, right? Delta R over delta T as delta T shrinks to 0 is dV, dr dt. dr dt is just velocity. And so we have V over R times what in the limit becomes instantaneous velocity. So we have V squared over R. All right. So that's where that formula comes from. What are the implications? Remember, we just said that centripetal acceleration changes the direction of the velocity vector, whereas tangential acceleration changes the magnitude of the velocity vector. So now let's consider our old friend of an object launched horizontally off of a tabletop. Right? The only acceleration at first is, well, actually, the only acceleration period is that of gravity, and that points straight downwards. So at the instant that it's launched, the velocity is purely horizontal by definition, by our design. We've launched it purely horizontally. So the acceleration, which is purely vertical, is a purely centripetal acceleration, right? Because it's perfectly perpendicular to the motion. And that was our definition of a centripetal acceleration. The only, and that effectively only changes the direction of the motion, because that's what centripetal acceleration does. To put it another way, our current motion is in this direction, in the horizontal direction. So that's the tangential direction, the direction along that of instantaneous velocity. And perpendicular to that was the radial direction. Even though we don't have a obvious circle here, we don't have a circular track or anything like that, the radial direction is just defined as the direction that's perpendicular to the tangential direction, which is the direction of instantaneous velocity at that moment. And here it's horizontal, so the centripetal direction is vertical. But as soon as the ball is launched, because it was originally horizontal, but the centripetal acceleration is attempting to change its direction, as soon as that direction changes even the slightest bit, that velocity now has a vertical component to it, right? It's no longer purely horizontal if that direction is being changed by a downward pull. So whereas before, so these purple arrows kind of indicate where it was the last time step. At the last time step, it was purely horizontal. At the next time step, it's now got a downward component. So the direction of motion is increasingly more and more towards the vertical. So the vertical acceleration due to gravity becomes increasingly tangential, right? Because tangential is now pointing almost perfectly vertically, so a vertical acceleration due to gravity is almost completely along that direction. It becomes increasingly tangential, which by definition means it is becoming increasingly less centripetal. So accordingly, the change in the velocity vector goes from being mostly directional. Here it's not changing the magnitude very much, but it is changing the direction by quite a bit between the steps. Eventually, when this thing becomes nearly vertical, well, you can't keep changing the direction by much because it's already nearly vertical, which is the direction it's trying to pull it into. But it does start to change the velocity more and more and more as it speeds up increasingly more as it falls. Okay, so that is all about centripetal acceleration and tangential acceleration. And now it's actually quite straightforward to talk about centripetal force.